Okay, today let's look at our three different types of geothermal energy. So if we name them all, I think we'll start with the first one, and it is a hydrothermal, or sometimes it's called HSA, which stands for Hot Sedimentary Aquifer. So if we're thinking about a hot sedimentary aquifer, I guess we've got to define our key word here, and that is an aquifer. An aquifer, well, an aquifer is a porous rock, a rock that allows water to flow through it. I shouldn't say porous, I should say a permeable rock. So an aquifer is a permeable, we can also say a porous rock that allows water to flow through it. If we think about what that would look like in some sort of scale, we might have a small section of rock here, and here's all the different sand grains. Some of them are touching. I have a rock, oops. Colour those in. This is obviously two-dimensional. Three-dimensional would look a lot different. And what happens here is water flows through these pore spaces. So if we think about the type of rock that might have these sort of grains, you're thinking of a sandstone or a limestone. And sandstone is most often, particularly here in WA, it's our most common type of aquifer host. Sandstone. Water flows through gaps. So permeable means the rate at which water flows through, and porous is the amount of air holes in it. So they are two different words, but an aquifer really is a rock that has water in these small spaces. Now, when we're thinking about HSA and hot sedimentary aquifer, well, we've got our aquifer, and a lot of these exist on the surface, but because they are quite close to the surface, they're not very hot. So we need to get these hot. So how do we make something hot in nature? We bury it deep. So an aquifer that is buried deep contains water at high temperatures and at high pressure. Now that's going to be really good for us. Quite simply here, a borehole is drilled into the rock. Let's draw this on the surface. So we're going to draw our surface here. And we might have some layers of rock. We might have some layers of other type of rock. And then we might have what we're going to call a confining layer. And then underneath that, we're going to have our aquifer. I'm going to draw it with these little dots here. And they're going to represent all of the little droplets of water that's stored within the rock. Hot aquifer. Now the confining layer is really important because it stops the water migrating to the surface, which allows it to stay down here at depth, getting really, really hot. Why is it hot? Because of the geothermal gradient. So all that we have to do now is we have to build our turbine. So that might be a case where we have, I'm just going to draw this to represent the turbines, little circular turbines. And they're all attached to gears, which will then go to maybe a generator house. Turns a generator, and that sends off our power to our power lines. So we're going to have our bore, which brings water up from the surface. And this water is going to rise upwards. It's going to be hot enough to turn this turbine. Might release a little bit of steam too, which then turns the generator, which generates electricity. Now at the same time, we're going to remove that water. We're going to pump it back underground. Pumping it back underground is called recharge. I'll write this in black here. So let's write down what's happened. A borehole is drilled into the aquifer and the hot water pumped to the surface. So what are our requirements for this? Well, we need water. We also need an aquifer at depth. The only problem with this is that we are removing water from a natural system. Although we are having some sort of recharge, we are taking water out. So that can have an impact on natural environments, but generally this is a fairly closed system. So water is taken out and then water is pumped back in. So that's our first type. Okay, let's look at our second one. And our second, and third, we'll actually try and do both in this time. We're going to try and look at hot or dry rock, or sometimes it's called enhanced geothermal systems. So EGS, or hot rock, or dry rock. Now, it's dry rock because there is no water. So there's no water at that location. It is hot rock because these particular rocks will have radiant energy. There are rocks that So hot rocks, because they are rocks that have heat energy caused by radiometric decay. So a good example of this is granite. So granite has uranium and thorium in some small amounts. So we have all this heat, we have it deep down, but we need water. So what do? We've got to pump water down into the rock. This is where it comes to our next little part, which is hydrofracturing. Hydrofracturing is the process where water is pumped under really high pressure deep into the earth. So high pressure water is pumped underground, creating fractures in the rock. We do this is done to allow subsurface underground, subsurface materials such as natural gas, petroleum, and water flow out or escape easier. Fracturing is used mainly in oil and gas. You might have heard also fracturing used in coal seam gas. So high pressure water is forced underground and it cracks and breaks open and causes lots of micro fractures within the rock, and that allows all of those materials to flow out of the rock a lot easier. Water is then pumped down where it's heated up by these hot rocks. What this means is we have a closed system. Everything's contained within a small area. The water that is used to bring the heat to the surface is then reused underground. Is reused. So let's draw what this looks like. Here's our ground surface here. And again, we're going to draw a little turbine, and a little generator, and little power lines. So here's our generator, and here's our turbine. So, often this is done at great depth. And the water that is here, the rock that is here is fractured. And these little cracks and little marks here is to represent the fractures. And what these fractures do is they allow water to seep into the hot rock. And it comes brought to the surface. However, I've not told you how the water gets there. Well, the water gets there because it's pumped again, forgive the really crude drawings here. It's one of those cracks. And water is pumped under pressure down, creating these fractures, heating up the water, which then is taken up to turn the turbine. And like I said, most commonly, the hot rock is granite. That's our heat source. So, what do we need here? What are our site requirements? Well, we need a hot rock. We need granite. But not just any granite, we need granite with a high temperature caused by isometric or isotopic decay. We also need water. And this is possibly our greatest problem here. It's because there is no local sources of water. It would have to be brought in elsewhere. Okay, let's do the last one. All right, our last one, our last little geothermal. We've just finished hot and dry rocks. Now we're going to go on to magma. So locations for this, I'm going to start straight away, are in countries where there is magma close to the surface. So if we look at a plate tectonic map, well, what places naturally occur? What places naturally occur that allow magma to rise to the surface? Well, you might think subduction, and yes, I think subduction boundaries might be a good location. We've got rising diapirs of magma, but the best is going to be divergent boundaries. So for two reasons, I'm going to say divergent boundaries, because there's an active source of magma. Because we've got divergent or splitting apart movement, there's a good chance that water is going to inflow into these depressions. So we've got water. There is another reason as well, and it comes to when we think about our volcanoes and lava. At subduction boundaries, we get very violent volcanoes and quite violent eruptions. However, at divergent boundaries, we have quite gentle volcanism. We've got, I'm going to write called gentle. We've got our low silica. And our gas pore. So there is a very low viscosity. Magma. It's non-violent. So if we were thinking of building a multi-billion-dollar geothermal energy plant, we want to do it in a place where there is not as much chance of it getting destroyed by tectonic activity. Okay, so what happens in this location? I'm going to draw it here. Here's our surface. Here's our magma. And to put it really simple, water is pumped into the ground. Again, fracturing can take place. However, in areas that are quite volcanic, if we think about the rocks that are there, we think about rocks such as basalt. And there is a unique property about basalt that you probably might not realise straight away, and that is it is vesicular. It has holes in it. Sometimes it looks a bit like Swiss cheese. And water can flow through that. So water is pumped down, where it is heated up by the magma and then brought to the surface, turned to steam and generates power. Best examples that we have of this exist in Iceland. Iceland has multiple geothermal energy power plants. So if we think about our site locations, our site criteria, we need area where the crust is thin, or volcanic regions. If you want to do a little bit of research, there's a place in Iceland called the Blue Lagoon. It's just outside of Reykjavik, and it's a wastewater plant. Wastewater is brought up from so water is pumped underground, used to turn the turbine at the geothermal power plant, and then the water that is left over contains a silica residue or a silica mud in it, and they store it in these pools outside of the power plant. And some people started to notice that it wasn't dangerous, so people started to swim in it, and if they found that a lot of their skin problems all disappeared, and it's because the rich silica mud, the wastewater from this form of geothermal energy, it was actually really good for your skin. And they formed a place called the Blue Lagoon, and apparently if you go there, well actually I've been there, and if you go there you can swim in the pools and rub your face with this magic silica mud that gets rid of all of your blemishes and pimples. It's great stuff. So what I definitely would like you to do when it comes to geothermal energy, not only do I want you to understand how it works, but think about the site locations and where in the world this could happen. What are the requirements that are needed? Tectonic requirements, and I guess how can you use tectonics or other data to identify places where there might be a good location to generate geothermal energy? Okay, thanks.